Yeah, great. Yeah, thank you very much, Ray. And yeah, thank you very much indeed for the invite as well. Just thinking it's kind of quaternary sort of science, I guess, is relatively new for me. But hopefully I can sort of talk about some kind of interesting things about, I guess, the history of the Greenland Ice Sheet through this time and maybe a little bit prior to the quaternary as well. And in particular, yeah, from sort of using some kind of stuff that we've been working on, thinking about the subglacial topography beneath the ice sheet today and what that can tell us about its history. So just a quick primer on Greenland, and this will be familiar to most people here, I'm sure. But essentially, the key question here is that with Greenland currently hosts the only ice sheet in the Northern Hemisphere, and as well as that, there's a permanent population of about 56,000 people in Greenland today, living around the ice-free margins, given that sort of about four-fifths of the island is currently covered by the Greenland ice sheet, essentially. And here we have about 3 million cubic kilometers of ice sat on Greenland, which is equivalent to about 7.4 meters of sea level equivalent here. So that's obviously a lot of ice, but it's actually kind of, relatively speaking, it's the junior ice sheet on Earth today. It's only about 10% of the size of the Antarctic ice sheet. But despite that kind of disparity in magnitude, Greenland is very much a major contributor when it comes to sea level change today. And this kind of graph on the left here shows through kind of ice mass balance calculations that Greenland is actually losing mass at a faster rate than any any of the ice sheets today, faster than Antarctica. And particularly over the last kind of 20 or 30 years, we've seen this kind of notable increase in the rate at which mass is being lost from the Greenland ice sheet. Such that today the Greenland ice sheet is the largest contributor to what we call barostatic sea level change. That's the sea level rise contribution from melting of land ice, essentially. And I guess the big question here is kind of, what happens to this curve, to this line beyond the end of the x-axis there. So what happens as we move into the future, the rest of this century? What is going to happen to the Greenland ice sheet? I think it's one of the kind of key questions that we face in the cryosphere science. And I guess the main tool we try to use to answer that question is to use numerical ice sheet models, which take essentially, in very sort of simplistic terms, an ice sheet model will take a number of physical processes which we think govern how ice sheets behave. It'll formulate a mathematical description of those processes, and it'll encode them in a computer code, and then apply that model to a particular problem. So in this case, that could be predicting how the ice sheet will respond to sort of ongoing and future ocean and atmosphere warming. And if we look at kind of comparisons between different ice sheet models, this thing is from ISMIP 6, so the sort of latest round of ice sheet model into comparisons. For Greenland, you can see in these two curves for low emissions in the blue and a high emissions scenario in the red, there's still quite a wide range of possible scenarios there. Different models have different predictions, which is to be expected. So there's quite a wide range of predictions here. And I think what we need to try and maybe do is think about how can we assess model performance. And if we want to understand how much we can trust a model to predict future change, we perhaps need to examine whether it can successfully account for past behavior of the ice sheet, which we maybe have some observational records or data for. And what we do know about the Greenland ice sheet is that it's existed through and probably prior to the quaternary. We do know that much, probably. But I think there's still a lot maybe we don't necessarily know about the Greenland ice sheet. I think its long-term history is still relatively poorly understood. I think there's still some fairly fundamental questions which we can't really answer definitively. We don't really know exactly when the ice sheet first formed, perhaps how big it was at that time, and we don't necessarily know how exactly it's responded to past periods of climate change through the quaternary. And that's often manifested in this kind of challenge where you see, this is a few years ago now, this figure, but you see different kind of ice sheet climate models producing quite a wide range of different kind of ice blobs here on Greenland. These are all for the same time period, and you can see the model spread there between different ice sheet climate models there. I think this kind of fundamentally reflects, I guess, the challenges with kind of ice sheet climate modeling. It's a very difficult business, but I think also we need to try and have more database constraints of ice extent in the past if we are to improve our understanding of the history of the Greenland ice sheet, and then maybe be sort of more confident, I guess, in the sort of ability to model its behavior. So if we were to go about trying to understand and infer glacial history, how might we go about that? And if we were in a landscape like the British Isles, where I'm speaking from today, you would probably go and look at the landscape and you would say, okay, you can see a number of pieces of evidence in that photo, for example, which tell you that that was a landscape that was formed under the influence of ice at some time in the past. Landscapes often can kind of contain the signatures of their past glaciation. You can probably see a number of them in that photo. And this is a common approach, geomorphological mapping that's been used to reconstruct ice extent in areas that were once covered by ice sheets or ice caps, but no longer are. Okay, and that's obviously the case in North America, in Scandinavia, and Britain Ireland here. In Greenland, we're kind of dealing with the opposite challenge. So in these landscapes, we're looking at areas where there was once a larger ice sheet and there's now no ice sheet or a very small amount of ice. But in Greenland, we've got a large ice sheet today, and we want to try and know what was it like at a time, maybe when there was much less ice on Greenland. So we kind of got the problem's almost been reversed for Greenland. And the challenge there is we've got this big ice sheet, which is kind of inconveniently sat potentially on top of the land surface, which is the potential kind of repository for quite a lot of information about its history. So the way we can try and measure that landscape beneath the ice, and really this has been kind of over the last 20 or 30 years only, there's been a real sort of advance in kind of the amount of data we've collected from across the Greenland ice sheet to measure its subglacial topography. And this is primarily radar surveying. So essentially it involves survey aircraft like the one you can see here, flying across the ice sheet and emitting electromagnetic radiation, so radio waves, which can travel through the ice sheet, bounce back off the land surface at the bottom, and return to the aircraft. And because we know the velocity of radio waves in ice, and we can calculate the travel time for the waves to get back to the aircraft, we can very easily work out the thickness of the ice sheet and therefore the elevation of the bed at the bottom. And it's really, like I say, been the last kind of 2 or 3 decades that the amount of this data we have available has really sort of proliferated and allowed us to sort of have a real kind of insight into what's underneath the Greenland ice sheet. And the radar surveys give us the opportunity to kind of produce really nice figures that look like this. That's basically a cross section through the Greenland ice sheet there, and you can see as you go down from the ice surface, you can see all these internal layers in the ice sheet, and maybe some places where they're quite conformable, and some places maybe where they're not. And that could tell us something quite interesting about the dynamics of the ice sheet, the relatively recent history of the ice sheet. But if we want to go really far back in time, I'm thinking kind of hundreds of thousands, millions of years ago, it's really this bottom reflection that we maybe have the most interest in, which is the basal topography, so the buried landscape at the bottom of the ice sheet. And that's what I'll try and talk about in this talk, essentially. I guess maybe one of my slight bugbears here is that these radar data, which now we have quite a lot of, what we tend to do with them is we collate them together, we interpolate them onto a grid mesh, and we produce a digital elevation model for Greenland, which looks a bit like that. And this is then used in the models that are used to simulate ice behavior as a boundary condition, effectively. And that's a very important use for this data set, don't get me wrong. But I think one of the things that's maybe been underutilized about these data is that these measurements of the subglacial landscape themselves are actually a really underutilized source of information regarding the history of the ice sheet and the geomorphic record that it's left imprinted upon the landscape. So I think there's still quite a lot we can look at with these data sets. Here's an example of one which I'll be focusing on in this talk, which is NASA's Operation Icebridge survey. This is about 10 years worth of radar data that were collected across Greenland. And you can see in the image the flight lines there being kind of animated year on year. And in total, this campaign collected about 800,000 line kilometers of data, of measurements of ice thickness and bed elevation. And that's about 30 million or so individual point measurements across the ice sheet. So it's an incredible sort of rich amount of data we have at our disposal here. And the question, I guess, is, can we start to use this database in a more systematic way to map the subglacial landscape and try to constrain something about the history of the ice sheet? And I guess that then follows on to the question of, given the size of this data set, can we start to think about, are there ways that we can use relatively simple, kind of automated or machine learning type approaches to maybe extract some patterns from the data set that maybe are more difficult to do manually? I think that's one of the questions I want to try and explore a bit in this talk as well. So I want to kind of split this into 2 and a bit parts, essentially. The first part I'm going to talk you through is an approach we developed to try and automatically map some particular features across the Greenland ice sheet bed, namely subglacial valleys, the valleys you see underneath the ice sheet. And then I'll move on to thinking about what we can learn from that about maybe processes of landscape evolution and ice sheet history later in the talk. So for this first section, I want to sort of just walk you through the process we use to try and develop this approach and how we quantify some of the spatial patterns we see in valleys and valley morphology across Greenland. And then maybe how we think about classifying the valleys according to how they maybe look compared to other valleys from other parts of the world, or the Northern Hemisphere anyway. So that's what I'll talk about for the next little bit. So, I mean, maybe, some of you may be familiar with this, but maybe others not. It has been known for a while that there are some quite interesting and quite large subglacial valley systems beneath the Greenland ice sheet. This has been published a few papers in recent years, which have sort of been quite headline grabbing, I think, and show that there are these quite dramatic valley systems underneath the Greenland ice sheet today. In many places, they're more than a kilometer deep. So these are quite large features. But perhaps what's less well known is kind of what their pattern looks like across the whole island and what these valleys actually tell us about the history of the ice sheet has perhaps been a bit less clear. We know they're there, but perhaps not exactly sure exactly where and exactly what they look like and what this means. So that's kind of how this work started, really. And I guess the kind of motivation here is almost if we go right back, and most of you will probably have done something at high school kind of geography level where you'll have learned the difference between, a valley which forms maybe in the absence of ice, so like a river valley, which maybe looks like a bit of a V shape, like that. And then as you go kind of through glaciation, the valley might look a bit deeper, wider, a bit more like a U shape. And fundamentally, the morphology of the landscape and valleys can change depending on the imprint of glaciation or not. I think it's fair to say that this kind of simple, V versus U-shaped valley sort of paradigm, if you like, is oversimplified, and there's many things that can control what valleys look like. But I think what this does demonstrate is that the size and the shape of valleys can tell us something quite informative about the erosive process or processes that might have formed them. And that's kind of something that I want to kind of, I guess, take advantage of here. So what we essentially did with this bit of work is we tried to come up with a few metrics which we thought could capture, I guess, the morphology of valleys in a relatively simple quantitative way. And the four we settled on are these four here. So we have essentially a measure of the valley depth, so simply the distance between the top of the valley and the bottom. The width of the valley at the top, so from rim to rim, essentially. Then this thing called the V index, which is essentially just a measure of the cross-sectional area of the valley and how it compares to like an idealized V shape, if you see what I mean. So the more the kind of valley profile deviates from a V shape, the higher its cross-sectional area will become, and therefore the higher this V index will become. And then also we look at curvature as well, the sort of the curvature of the valley walls, and particularly how that varies as a function of the sort of scale of investigation. So as you sort of look at the valley kind of more widely, how does the curvature change compared to when you look at the valley, just the central part of the valley, essentially. So these four metrics together can tell us maybe something about what valleys look like in a sort of quantitative way. So we took those four metrics, and I'm going to sort of chat maybe at the end about how we settled on those four. But for now, we sort of took those four, and we basically extracted as many valleys as we could from all the radar data across Greenland in a sort of automated way to sort of, isolate valley features and basically take a radar image like this and convert it to a profile of the valley cross-section like this one here. And we found about 5,000 valleys in total across the radar data set, but for Greenland, so quite a lot of valleys. And we calculated those metrics, those four metrics that I showed in the previous slide, for each valley. And that gave us a map that looked like this. Here's just a couple of the metrics shown here. And I think it's fair to say that if you look at that image, you might think that's a real mess. There's a lot of color going on there, and it's kind of hard to really understand what that's telling us. I think that'll be a very fair reaction. I think when we sort of saw this, we weren't really sure how to interpret that. And there's quite a lot going on there. It's quite a busy plot. But I think what it helped us to sort of think about is, how can we compare the morphology of the valleys we're seeing underneath the Greenland ice sheet to maybe valleys we see in analogous areas elsewhere in the Northern Hemisphere. So, and that maybe helps us to kind of interpret these patterns in the context of landscape evolution. So what we essentially did here is we built a training data set from valleys from other parts of the Northern Hemisphere. And we deliberately chose half the sites with no history of glaciation, from sites like the Appalachians, from the Sierra Nevada, from the Atlas Mountains in North Africa, and also half the sites where there's a significant Quaternary glaciation history. So, the European Alps, the Rocky Mountains, the Scottish Highlands, and in Scandinavia than in some of the highlands in Norway. And what you see if you plot those valleys into sort of this morphometric space, so these different kind of morphometric indices for valley morphology, you can see that the reds, which are the glacial sites, and the blues, which are the fluvial sites, do sort of separate out quite nicely in this morphometric space. So in other words, valleys from these different sites do have quite distinct morphologies, depending on whether there's been glaciation or not glaciation. You can see that the V index and these different kind of measurements tend to be more characteristic of one or the other in many of these places. So that's quite useful to help us try and sort of understand um, or translate, if you like, the patterns that we see in Greenland to maybe start thinking about processes of formation rather than just morphology. And that's the training data that we can then use to sort of train supervised machine learning algorithms, essentially. So the algorithm that we chose for this was random forest, which some of you may well have come across. And essentially, the idea behind this is the random forest is built up of a lot of different decision trees. And the decision trees are simply binary trees which will ask kind of, does the valley have a depth bigger than 1 kilometer? Yes, then it's more likely to be glacial. No, it's more likely to be fluvial, etc. And it's built up of a number of different those sort of branches in the tree. And the random forest just generates a lot of trees, which are all sort of subtly different from one another to help kind of get around the problem of maybe overfitting the data if you only use one tree, for example. And the power of the random forest is also that with a lot of trees, you can then have a sort of majority voting system where each tree will vote for the kind of for a particular valley. It'll sort of based on a number of different questions. It'll ask, is it glacial or fluvial? And given all that sort of voting, you can pool the results and ask, which received the majority? Did more trees go one way than the other? And how big was the majority? So maybe tell us something about kind of the confidence which we can have in the classification, essentially. So it gives us that ability to kind of measure or to kind of estimate the likely, I guess, formation process of valley formation relative to known valleys, which we have a known history for. And if we then plot that out in Greenland instead, so now I'm plotting on the left, reds are essentially valleys with a high glacial score from the classification, and blues are valleys with a high fluvial score from the classification. Okay, so hopefully you can see, generally speaking, that the valleys, and I'm sort of in the plot on the right there, I've also kind of just interpolated that to make it a bit less messy, and you hope you can see some of the patterns coming out a bit more clearly. And I think, again, there's still quite a lot going on in those maps. But I think one thing I want to draw your attention to is that there's going to be quite a lot of red around the margins as a rule, which maybe you would expect given the kind of contemporary fast-flowing ice you see there. But also you see these quite strong red colors in the eastern parts of Greenland and the southern parts of Greenland here, compared to maybe the more blue, more fluvial kind of classifications you're getting in maybe the western and the central areas and in the north as well. So those kind of patterns maybe tell us something about the sort of the history of the landscape in these different areas as well. So I think, and again, there's a lot of things I could focus in on in this talk, but I think for simplicity, I want to sort of stay focused on, to begin with at least, these kind of areas in the high areas of eastern and southern Greenland, where you have these quite strong red colors, these quite strong glacial classifications. And the reason this is quite interesting is that there is a potential kind of problem here in that many of these valleys, these let's say glacial valleys, the valleys classified as being glacially formed, are found in areas today where we actually wouldn't expect particularly fast or erosive ice to be. They're often beneath quite slow moving ice, kind of in those sort of more interior regions of the highlands, and also ice which is thought to be cold based, so essentially frozen at the bottom. And the combination of very slow and frozen basal ice is essentially very unlikely to cause much erosion and much more likely to be preservative of the landscape. So we have kind of glacial landscapes or valleys which are formed by ice, but apparently unlikely by the modern ice sheet. So then we start to get into the kind of question of when these are most likely to be paleoglacial valleys, essentially. They must have been formed at some time when the ice sheet looked a bit different to how it looks today. So if we look at this map here, by comparison with the dynamics of the modern ice sheet, you can sort of divide the glacial valleys up into ones that we think can be contemporary and ones which are maybe not contemporary. And I think in this plot, the reds are valleys which are consistent with the formation beneath the modern ice sheet. So they host fast-flowing, maybe warm-based erosive ice today. And the kind of yellow colors here are the ones which I think are not consistent with the modern ice field. They're under slow-flowing, frozen, non-erosive ice today. And those clusters very much appear in the southern and eastern highlands of Greenland here, and parts of the north of the island as well. So are we seeing kind of hallmarks there of a landscape that is effectively kind of frozen in time, if you like? It's a landscape that was formed at some time in the past, and because of the kind of nature of the ice sheet today, it's been preserved from erosion by slow-moving, stable cold-based ice today. So I think that's kind of the main, I guess, thing we can be take from that pattern, or at least what I want to focus on for this talk now is to kind of focus a bit more on those valley systems in these eastern and southerly regions of Greenland. And particularly in this part, I want to think about what that actually tells us about the history of the ice sheet. Can we understand something about the ice sheet configuration that might have eroded these features? And by doing that, can we gain some insights into when this incision might have happened and what the climate might have looked like in order to kind of have an ice sheet of the scale necessary to form these features? So the second part of this talk relies on a second method, which I'm going to very quickly introduce, which is there's an alternative way to map valley systems across Greenland, or at least parts of Greenland. And this relies on the fact that the ice surface, so the surface topography, in subtle ways can often mirror the bed topography, the topography at the base. In other words, the ice surface is a bit of a sort of a ghost image of the bed topography, given a relatively stable and slow-moving kind of glacial regime. And hopefully in this image here, which is a kind of basically a hillshade type image of the ice surface, you can sort of see some features maybe down here or in here, which look a bit like valley systems, just in plan form. Okay. And if I kind of if I sort of show on the mapping that we put on top of that, that's kind of the sort of the plan forms we've been mapping out here. And if we compare that to where the radar lines detect the valleys, you can see that they often do align with these features in the ice surface imagery, which is, I guess, reassuring and sort of shows that actually by using these two methods combined, you can actually learn something about not only the cross-sectional geometry of their valleys, but also their 2D plan form from above. So you can get more of an understanding of what the structure of the valley network actually looks like. And if we take that and apply that to the whole kind of region of the south and east of Greenland, we get this sort of pattern that we map out in the subglacial valleys across these regions, which we saw first in the radar data, and now we can also map out in the ice surface imagery. I think what I want to point out here is that there's some quite interesting patterns in these valley plan forms. They're divided into two colors. So the purples are valleys that are oriented eastwards toward the coast, and the greens are valleys which are oriented inland, so facing kind of away from the Atlantic coast today. So as well as that kind of, I guess, divide in terms of where the valleys appear to be oriented, we also see some quite interesting evidence of dendritic patterns, like you see in some of these valleys here. So these sort of branching networks. We see radial drainage patterns, for example, over here. And we see valleys which cross-cut modern-day ice divides. And I think all of these observations, again, are consistent with this idea that these valleys cannot have been formed beneath the modern ice sheet. This is just not the sort of network you'd expect to find forming beneath a large-scale ice sheet like we see in Greenland today. This is much more reminiscent of a more sort of mountain-scale glaciation, which maybe even overprints a pre-glacial inherited fluvial network, which kind of has some hallmarks left over in perhaps some of these sort of branching patterns, which you would associate with river systems in upland areas as well. So I think we can quite confidently sort of suggest that these are not contemporary features. And that's also borne out by this examples like this profile here, where you see these kind of large, what are classified as glacial valleys through the highlands here, but there's very little ice flowing through them today. There's maybe sort of less than 20 meters a year of ice flow, which is pretty slow for glacial ice. And there's no evidence that flow is being steered at all through the valleys. It's pretty much sort of low everywhere. So these valleys, sorry, are not kind of consistent with modern day ice sheet erosion. And I think they're much more likely to have formed when you had a scenario where there were smaller ice fields or ice caps present in these parts of Greenland, with flow which must have been sort of radiating out from sort of central divide, which caused the kind of patterns you see with ice kind of converging these sort of dendritic networks, and sort of some facing toward the coast and some facing towards the interior of the continental of the landmass. So I think we can then ask, okay, so we've got this pattern which is suggesting that there's a landscape here which was formed by mountain scale ice at some time in Greenland's past. So then we can ask, can we think about growing an ice sheet with, or can we try to using a sort of simple ice sheet model setup, can we kind of try to grow an ice sheet with a configuration that maybe matches those paleoglacial valleys? Can we sort of form something that is broadly consistent with what we see in the geomorphic record there? So the way we've done this is a very simple ice sheet model experiment, which we just set up using the parallel ice sheet model. And in this, all we do is just vary the climate. We vary the temperature across Greenland with a few different sort of configurations. And we vary the precipitation as well. So we think about kind of how the precipitation varies across Greenland. And it's a very simple approach where we sort of assume that temperature kind of varies with latitude and with altitude. So it's kind of just really sort of simple, almost back of the envelope type ice sheet modeling. Just sort of think about what sort of conditions could be capable, if any, of forming an ice body mass of the sort of scale you would need to form these features that we see. So to do this, like I say, we use the parallel ice sheet model and we grow ice on a pre-glacial land surface. So beginning with no ice and sort of starting from scratch, essentially. And we want to try to identify, can we find any climate conditions that maybe do match or don't match the observed valley extent you see from the geomorphology. We ended with this sort of this little matrix essentially, and this is just for varying the two parameters in the temperature field. So I think across the top we're varying what the sort of the mean annual air temperature was for sort of the Greenland, and on the y-axis we're measuring how strong the gradient is from south to north. So it's just these two parameters which sort of govern what the temperature distribution looks like across the island. And you can see the ice sheet that's produced as a result of each of those configurations. I think in these plots, hopefully you can see there's some black outlines there, which kind of have outlined the approximate extent of the valley networks we've mapped in the east and the southern highlands. And so you can see that some of these ice bodies maybe match the distribution of the kind of valley networks relatively well, and some don't. And if we kind of look at the goodness of the fit, if you like, between the observed and the modeled ice extent, we end up with sort of identifying like the best fitting kind of combination of parameters which can fit the extent of the model, the extent of the observed valley networks, and therefore maybe the extent of the ice sheet that we needed to have formed them. One of the interesting results that pops out of this is that there is a slightly different best fit for the east compared to the south. So the south, you need basically sort of slightly cooler temperatures to get the fit compared to what you do in the east. And there's perhaps, this is a slight aside, but there's potentially an interesting difference in the glacial history of these two regions, which I've sort of been lumping together up until this point. But actually what we find is in the east, compared to the south, we find that actually in the southern parts, the southern highlands here, the valleys tend to be less deeply incised, you can see here, compared to in the eastern highlands. And that's kind of the same regardless of the geology. So it doesn't seem that geology is a key control on the valley depth here, but rather it's kind of a difference between the south and the east. And the south also contains a greater proportion of valleys classified as fluvial in our classification scheme. And I think maybe together these observations suggesting that the southern highlands might have been less heavily modified by mountain scale glaciation. There's sort of slightly less intensity to the erosion here. It might be that's telling us that glaciation in the southern highlands happened for less time. Maybe it started a bit later. And that would probably be consistent with the idea that the southern highlands are generally a bit lower in elevation and they are lower latitude as well. So maybe more likely to be warmer than the eastern highlands, and that could explain the difference in the best fitting temperature that's required to fit them in the previous slide. There's potentially a sort of subtle difference here in what happened in the east compared to what happened in the south, but maybe more on that at the end. So I'll show you here just to zoom in of the best fitting model output. The sort of the model output seems to sort of best fit the nature of the highlands there. The valleys there in the highlands. And you can see we get these kind of sort of mountain ice field type bodies, which would be much more capable, essentially, of forming the types of landscapes we see in these areas, with kind of ice velocities focused through the valleys that you see in these areas, and sort of maybe warm-based erosive ice focusing through the valleys, causing them to be eroded, with maybe more cold-based ice present on the mountain peaks or in other areas, which might preserve some of those remnants of the inherited pre-glacial topography that I think we do still see hallmarks of in that landscape there. So you can see that sort of radiation of velocity out from the central divides along the mountains through those valleys. And I think these bodies will be much more capable of incising the valleys, but while also protecting adjacent areas from erosion. Just for reference, the total ice volume containing these bodies is about half a meter of sea level. So it's only about maybe 10%, maybe a bit less, of the volume of the modern day Greenland ice sheet that we're seeing here. Yeah. So I think in the final kind of few slides, I wanted to kind of maybe do a bit more speculation and think about what could we say about when these valleys might have formed. I think we can say quite confidently if they didn't form recently and they're not contemporary features, they're much more likely to be sometime in the past. The question is kind of when in the past, what might they have formed? So the figure here is just, or the image here is some southern Patagonia, I think, and that's just kind of something that's a bit more like what we might have expected Greenland to have looked at the time these valleys were being formed. So I think the question again I would get onto is how how old might they be? Unfortunately, the subglacial landscape in itself is not a chronometer. We can't really tell anything about age directly from the observations that we have. But maybe we can say something based on the kind of climate we've been using to model those ice sheets. Can we say anything about approximate timing or relative likelihood of certain periods? So if we use our kind of our geological timescale here, this is a temperature record through the Cenozoic. And if we kind of particularly interested, I guess, in times when the ice sheet in Greenland was smaller than it is today, and particularly in the context of future climate change, as you can see here, the first obvious candidates to look at would be the interglacial periods of the Pleistocene. So these relatively warm periods where temperatures were elevated relative to today. And we know the ice sheet, both in Antarctica and Greenland, was probably smaller than it is today, and sea level was higher. But the question is, could it have looked like these valleys imply it might have looked during these times? I think if we look into I guess the last interglacial first, so the Eemian, I think that seems a bit less likely. If we look at kind of various model outputs for the Eemian Greenland ice sheet, you can see that although potentially there could have been some quite significant mass loss in places, models consistently produce ice sheets which are still quite a bit larger than we would need to have formed these kind of paleoglacial valleys in the east and the south. And the models suggest that most of the ice sheet kind of still did survive. There's still like a core of a quite a large ice sheet present at this time. And I think generally speaking, sea level records for the Eemian probably imply there wasn't really enough ice mass loss at this time either. We would need kind of at least probably 7 meters from Greenland to kind of make that work for the modeled ice sheets we're looking at. And we don't really see any evidence for that at this time. And I think also we do see there is some last interglacial ice preserved in ice cores in parts of the north and east of Greenland, which implies that ice persisted in those areas at that time. So I think we can fairly safely rule out the Eemian. But then we've got also other interglacial periods during the Pleistocene, where more ice loss occurred in Greenland. And this paper a few years ago from Jörg Schaefer and others, which kind of showed that using a drill core record from the center of Greenland, so the GISP2 ice core, and from the cosmogenic exposure dating from radionuclides there, that they concluded that kind of at least on one occasion in the last million or so years, central Greenland must have been ice-free. And for that to have happened, you would need to have a relatively modest amount of ice just persisting on the highlands in eastern and southern Greenland to make that the case. This might have happened only once, but it may have also happened on a few occasions, perhaps during the particularly long-lived or warm interglacials, perhaps, for example, marine isotope stage 11 or 31, which are often kind of cited as these larger sort of super interglacials of the Pleistocene, where ice may well have been confined to these regions. And these kind of models, these are just sort of relatively schematic models, but they do kind of resemble what we're sort of seeing in our work as well. And it may well have been the case that ice was confined to these parts of Greenland at this time. I think the challenge maybe here is that it's the question we have to think about is how much time would we have needed to have incised and formed the landscape that we see in the southern and eastern highlands of Greenland today? Would one interglacial period have been enough to have kind of formed what looks like quite a well-developed glacial mountain landscape? Maybe it would, but maybe we also need to be thinking about a longer period of time, or maybe times earlier in Greenland's history as well. So I think we certainly can't rule out these kind of these major interglacials, but perhaps they're not the primary cause. I think it's hard to say exactly. So if we want to kind of move back beyond the Pleistocene, and so this is kind of taking the only major diversion, hopefully, out of the Quaternary, the obvious other period to look back to would be the Pliocene, so back beyond sort of 2.7 million years ago, a time when we know CO2 levels were higher than or comparable to today, often held up as a kind of an analog for the future. And this mid-Pliocene interval, there's certainly been more uncertainty as to about whether there was major ice in the northern hemisphere at this time, and if so, what might it have looked like? So what can we say about the Pliocene here? Well, in ice sheet models again, you can see on the left here, this is a plot of a sort of a heat map from ice sheet models for the Eemian, and we can see that generally speaking, there is quite a lot of ice present in the last interglacial for Greenland, which doesn't really match up with the observed extents from our mapping. But if we look at the mid-Pliocene warm period around about sort of 3 or so million years ago, models generally produce something that does look a bit more reminiscent of what we see in eastern and southern Greenland, where ice might have been confined to these areas under a climate where temperatures perhaps sort of 2 to 4 degrees warmer than pre-industrial, and indeed ice may have been restricted to these areas, which may be more is more consistent with what we're seeing in the geomorphology as well. So the Pliocene is looking like a possible target, possible time period for the formation of these networks. It's really hard to sort of say a lot about Pliocene climate in Greenland. The evidence is yeah, there's not a lot of evidence for terrestrial Pliocene climate at this time. One thing I can sort of show here is that on this graph I've sort of shown the blue line here is the modern temperature gradient for Greenland in sort of quite schematic way, but you can see the blue line representing the modern temperature gradient for Greenland latitudinally, so from the bottom of Greenland about 58 north to the top of Greenland about 84 degrees north. And the red line here is the best fitting gradient which we use from our ice sheet modeling. So that's the kind of the gradient that you would need to assume to produce the kind of ice fields that you see in the southern and eastern highlands that we've mapped out in this work. And if we compare that to a couple of examples that we have from the terrestrial record and sort of Pliocene vegetation assemblages from northern Greenland, you can see, I think in here, I think this is like a fossilized ant head. Hopefully you can sort of see that there. I think it's facing upwards. And these assemblages have been used to sort of to infer some quite broad, like mean annual air temperatures for northern Greenland. So from those assemblages, but also from fossilized tree wood as well from the north of Greenland. And generally speaking, I've got about 2 data points here, but I guess I'm not going to draw any sort of strong conclusions from this, but they are sort of relatively consistent with the types of temperatures that we're inferring to have been necessary to have modeled the extent of the ice that we're seeing evidence for in the east and the south of Greenland here. So I think we can sort of say the Pliocene is a possible time for the formation of these valley networks as well. And I think that generally does make sense in terms of thinking about the early growth of ice in Greenland as we sort of see cooling through the Pliocene with obviously those warm periods interrupting it. You could have had mountain scale glaciation happening in the Pliocene in these parts of Greenland before the big expansion of the ice sheet kind of starts to happen as you move toward the end of the Pliocene and into the Pleistocene. And maybe we're seeing the kind of remnants of that early inception of the ice sheet with potentially some input from retreat periods happening during the Pleistocene as well. So I think that pretty much kind of brings me to where I wanted to leave this. I hope that's kind of, I hope I've sort of not gone through too much ground too quickly there. But I think I want to finish with just a few kind of key takeaway messages. And I think this is that one of the kind of key things we've found here is that we see these valleys in the eastern and the southern highlands of Greenland, which are quite distinctly glacial in their morphology. They look like mountain glacial valleys, but many are not formed beneath the modern ice sheet. They're just not consistent with what we expect to see beneath the modern ice sheet today. So how were they formed? I think it's very likely that these were incised by mountain glaciers, sort of mountain ice fields, which were exploiting an existing inherited fluvial network that would have existed prior to the glaciation. And they're now very well preserved beneath frozen, slow-moving basal ice in these parts of Greenland today. I think it's most likely that these features are the geomorphological remnant of a past or more than one past restricted configuration of the ice sheet that existed during warm climates of the past, which must have been warmer than today. And at this time, whenever it was, the barocentric sea level contribution of Greenland must have been about 7 meters higher than today. There was only a relatively small amount of ice present in Greenland when these landscapes were being formed. As to when, I think our probably best guess at the moment is these are likely to be valleys and landscapes which are associated with the initial growth of mountain scale ice in Greenland, probably at least 3 million years ago. I think the jury's still out on whether you had ice earlier in the Pliocene in Greenland, maybe even into the Miocene. And there's some kind of marine evidence we can have a chat about as well and think about what that tells us about the glacial history of Greenland at this time. And these features probably likely were forming prior to the kind of coalescence and the expansion of a continental scale ice sheet across Greenland. But I think, like I said, we definitely can't rule out the possibility that during particularly warm parts of the Pleistocene, the Quaternary, that there could have been more restricted ice again in Greenland, and that these kind of this state of the ice sheet could almost become like reoccupied essentially. And it's interesting to think about from the landscape. We see these restricted valleys and networks being the hallmarks of a kind of one state of the ice sheet, and then we kind of see the kind of fully glacial kind of continental scale signature of the ice sheet as well around the margins, which maybe suggests that there's kind of almost like two fundamental kind of constraints the ice sheet occupies: the kind of more restricted mountain scale one, and then it kind of expands out relatively quickly to a more continental scale one like we see today or during the LGM. And the transition between the two doesn't appear to have had a major erosional modification on the landscape. So whether we're seeing transition between the two happening relatively quickly or non-erosively, I think remains to be kind of looked at more, but I think could be quite an interesting question to think about as well. I think I'm out of time, and my voice is going a bit of a cold this week, but hopefully that kind of made sense. And I'm very happy to take any questions. Hopefully we've got some time left. So thank you very much for listening, and I'll shut up. Thank you.
Okay, Guy, thanks very much. That was very interesting. I'm going to ask the Bergen group first if they have questions, but while they're getting ready to ask questions, I want to ask you, I want to go back to the beginning of your talk when you were describing how you use the radar image to characterize the valley morphology. Wouldn't that require that each transect be orthogonal to the valley? I mean, what happens if it's sort of almost down the valley?
Yes.
How do you figure that out?
Yeah, absolutely. Yeah, that's a great question. Yeah, so we had to think about this, particularly when we're kind of trying to quantify how the valleys look. We want to be sure that are we actually sampling a relatively orthogonal profile, or not. So yeah, so the way we basically did this is we looked at the landscape on a sort of more on a large scale level, and we sort of calculated the expected kind of direction of kind of routing through the landscape. So tried to work out what the orientations of the valleys must be from the kind of larger scale sort of structure of the topography. And from that, we would sort of work out approximately kind of what the intersection angle between the kind of valley trends and the radar flight lines must have been. And we could essentially sort of say that if that angle was kind of too oblique, we would have to kind of ignore that and not basically not extract that as a valley. We could sort of choose what threshold we use exactly for that. I think we would use sort of 30 degrees or something like that. But if we think it's less than that, we take it forward. But when we came to calculate things like the valley width, we could then do a relatively simple kind of trigonometric adjustment for that angle not being orthogonal to try and I guess correct out for the fact that the valleys would probably be appearing if the orientation wasn't quite orthogonal, the valleys would appear wider than they truly are. I think so. That's kind of what we tried to correct for. But yeah, definitely an imperfect science. But yeah, that's kind of what we tried to do.
Okay, that explains it. Thanks. So we'll hand it over to Andreas in Bergen and the class there if you have questions.
Yes, we were wondering, the article states that there's very old ice in the inland turning East Greenland Highlands. Do you have any estimation of how old this ice could be, or how old?
Yeah, it's a good question. So I think one of the things we sort of tried to sort of conclude here is that if one would want to go to Greenland and try and find some quite old ice, I think, and those who scroll back here, yeah, one of the places you might want to think about that could be promising would be maybe some of the areas that would have been on the inland side of these early ice fields in the past, particularly because if ice has persisted there during both this state and also the expanded state of the ice sheet, you could potentially get ice surviving there for quite long periods of time. But also because it's so slow moving and static today, it wouldn't be being kind of evacuated out to the coast as you see on the other side of the mountains on the Atlantic coast. I think the question about how old it is a really interesting question. I don't have the answer, unfortunately. But I think that'd be one way of really getting to the question of how old is this landscape, and if you could drill maybe some of these subglacial valleys on the inland side and try and see how old is the oldest ice there. If it goes back through a few glacial cycles, what does that tell you about how the longevity of kind of ice masses in this region and when this landscape might have formed? I think is a really interesting thing that we could look at. Unfortunately, I don't have an answer as to how old it could be, but I think we do know that ice in Greenland, there's definitely some ice from, I think, marine ice up stage 11, so sort of maybe 400,000 years old in Greenland, and maybe a bit older. But I think we could well see ice in some of these areas that might actually be older than that. But that's just a guess. I don't have an answer, unfortunately.
Okay, thank you.
Just to follow on from that, could that ice be outcropping, so to speak, in the modern glacial Gemini?
I'm honestly not sure. I think it would be. I have to sort of think about kind of what the sort of flow patterns would be to get the ice from where it might have been forming to where it would be exposed at the margin today. I don't think there's certainly not been anything sort of found that's kind of that age, but I'm not sure, I'm afraid. That's the answer.
Okay. I think there had been some work done like that in Antarctica. Anyway.
Yes.
Okay. Questions? No more questions from Bergen then? And we have a question here, I think. Go ahead.
Okay.
I have to unmute you.
Yeah. I think.
How do I unmute you? Ask to unmute. Go ahead. Go ahead.
I think talking to the okay.
Go ahead.
Hi, I'm Danielle, not Ray. I had a question on your random forest machine learning approach. So obviously you were looking at different areas around the world for fluvial and glacial valleys and whatever. So I guess maybe I'm just trying to understand more about this machine learning.
Yeah.
And like, how can you make the assumptions of these erosive details from other areas like in Africa or other like mountain valley glaciers and apply it to Greenland when obviously there's different microclimates and which overall affect the erosion, I guess. So I don't like there must be like a error or like uncertainty going on, right?
Sure. Yeah. Absolutely. I think that's a great question. So I'll try and kind of explain a bit about how we sort of set this up and I guess the reasons we chose to do what we did. So essentially in these areas, I guess the main characteristic we were looking for is, are there landscapes we can be pretty confident about in terms of, did ice play a major part in making these landscapes look how they did today? And that's kind of how we governed which sites we chose for the training data set. And there's some examples we chose here, which I think are very distinctly fluvial landscapes in terms of what the valleys look like and how they clearly have formed. And there's others which are clearly glacial in terms of their history. The reason for choosing these particular sites, one of the reasons we did this, we want to try and minimize the amount of differences otherwise between these sites and Greenland. So we've chosen sites, from the Northern Hemisphere, and often these sites kind of share like a geological affinity with Greenland. So the sites, for example, in Scotland, in Norway, in the Atlas Mountains, these are all kind of part of the same mountain range of the Caledonian orogeny kind of hundreds of millions of years ago. So these are all geologically relatively similar areas, because obviously we know that one of the kind of key controls on what the landscapes looks like, and particularly valleys, can actually be geology, and we want to try and minimize the amount of other kind of variability going on there.
Okay.
So I think what this sort of plot shows is that if we look at the metrics we've selected, and we did look at a few other ones as well, but one of the reasons for choosing the 4 metrics that we chose is that, but for this train data set, they do sort of show those differences between the glaciated landscapes and the non-glaciated landscapes. And then it's essentially just a case of training the model on that data sort of to recognize, what are the diagnostic kind of combinations of metrics for glacial valleys and what are the diagnostic combinations for fluvial valleys, and then applying that to classify the Greenlandic ones. But one of the reasons that random forest is used here is that there is inherently uncertainty in this approach, and your training data, your machine learning model is only going to be as good as the trained data set is. So it's kind of the rubbish in, rubbish out kind of, I guess, mantra you maybe would say. And I think what we can use random forest to sort of do is to examine, because we've got like a large number of trees, you can use that to work out, are all the trees voting the same way, or do you get quite a big split between different trees? And if you are getting quite big split, what's that mean about the valley? Is it sort of plotting kind of right along the kind of intersections between the two classes, or is it sort of plotting out in no man's land where there's no actual data in the trained data? So we have to sort of look at that and sort of try and convince ourselves, are the results we're getting actually making any sense? And is the trained data set capturing the true variability of the Greenlandic valleys? And I think by and large we were able to sort of settle that it was, but I think that kind of required a bit of trial and error to get to that. Yeah.
Okay, cool. Thank you so much.
Okay, thank you.
Okay. Any other questions? Carly Prince has a question. I think I have to unmute you. Yeah, go ahead, Carly.
Can you hear us?
Yeah.
This is the group in Buffalo. Thanks for the great talk. I had a question, I think maybe starting on slide 30, you were showing the like temperature gradient between modern and what your simulation was. And you compared that to a potential gradient. Yeah, exactly. Nice.
Yeah.
A potential gradient like during the Pliocene. And
Yeah.
it made me wonder if you looked at other warmer than present time periods to like say like, well, can we consider / rule out like the Eemian, for example? Does that temperature gradient that presumably someone might have reconstructed, does it look similar to what you're plotting here or not, to say like which time periods in the past are potential candidates for a more erosive highland constrained configuration of the ice sheet?
Yeah, thank you. That's a good question. So the short answer, we didn't look at that too much. I had a quick look. I think the challenge is that kind of, actually getting reconstructed temperature gradients for Greenland or sort of these sort of terrestrial areas is not straightforward. So it's not easy to sort of find many kind of definitive gradients for Greenland in the past. I think that having been said, it would be very interesting to sort of look at some climate model output for these times and think about what do those gradients look like, and how much of a variation is there between these different intervals in the past, and how does it compare to the kind of the gradient that we have to infer from our analysis. I didn't actually do that. I think that'd be quite interesting thing to look at. All that I can say we did do is we also had a bit of a look at kind of actually periods further back in time as well. I had a quick look and sort of delve into kind of, was there any constraints on like temperature gradients for the Miocene or even earlier? Because there is a debate about, was there ice in Greenland as far back as then? I think the challenge there is that those gradients, those reconstructions, are very much kind of global in their nature and probably quite uncertain. So I think there's a challenge of, can you really apply a kind of continental scale temperature gradient to Greenland, where there might have been maybe more localized climate dynamics going on? The presence of an ice sheet, of course, would also affect the gradient there. So there's a bit of a feedback to consider. So the short answer is I sort of thought about it, and I've not really got anything more to show other than this. But I think it'll be interesting certainly to compare to some of the previous glacial periods and see how they plot compared to the modern and the Pliocene. Where do they fit into that graph there? Would be quite interesting. So yeah, thank you.
Yeah, great. Thanks so much.
Yeah.
Okay, Gif has a question. Gif Miller.
Great. That was a really interesting talk. I really enjoyed it. I have two questions, and the first one is simply, I didn't see that you'd use the Eastern Canadian Arctic fjord systems, which are some of the biggest in the world, in your comparison. And those really have to be major Laurentide ice sheet eroded, because there's no collection area behind the fjord systems really to build an ice sheet like you potentially have in East Greenland. But is there just no data that allows you to use those fjord systems in your comparison?
No, I mean there was. I definitely thought about that. I think one of the reasons that was slightly more difficult is that, I mean, actually it could be done now because we now have the Arctic DEM, which would allow us to get some good topographic data from those areas. I think one of the challenges with looking at sort of the fjord systems is, getting the topography of areas where you're on the coast and you've got sea level to consider, and do you know the bathymetry of some of the fjord systems as well. But certainly you could think about going onshore where the bottoms of the valleys are exposed. That's definitely doable. So there's no sort of fundamental reason that I didn't, and I think that would be quite interesting to add. It kind of would it kind of it'd be interesting to see if it filled any of the other sort of space in those morphometric plots that I was showing. But apart from that, I don't think to answer that. Yeah.
Okay. So, and the other one, this really intriguing idea of a non-Pleistocene glacial system, and the one thing you really need now with relatively small ice caps that you're positing there is you need a lot of time. But the Pliocene is a really long period, and when I think of, makes me think of like the Sierra Nevadas, which is relatively speaking a tiny spot, but you get classic glacial landforms of deep over steepened valleys. So it certainly makes it plausible that small ice sheets with a lot of time can do as much work as big ice sheets over a 2 million year period. But you really need multiple million year windows, I think, and the Pliocene has got enough time to potentially do that. So I thought that was a really intriguing idea of sort of counterintuitive to what we think of as warm time doing massive glacial looking erosion in Greenland.
Yeah, I think so. Yeah, I think that kind of question of how long you would need integrated, if you like, to form this landscape is a very interesting one. I think my impression is that it would be hard to imagine how you would do that in the Quaternary alone. I think you kind of have to look at that the Pliocene, or maybe even back into parts of the Miocene, to think about giving it enough time to form landscapes like that. So I think that's very true. Yeah.
Really great talking. Makes me think in a little bit longer temporal space.
Yeah, no worries. Thank you.
Thanks.
Okay. Well, with that profound thought, I think we'll wrap it up there. I'd like to thank you, Guy, very much for thought-provoking talk. Lots of nice, interesting data. And your recording will be on the website before too long. So thanks a lot.
Thank you.